Welcome to this video on oxidative phosphorylation. This process serves as the centerpiece of cellular energy conversion, facilitating the synthesis of ATP through electron transport and chemiosmosis, primarily for medical and biology students. Oxidative phosphorylation is the final stage of cellular respiration. Remarkably, it produces approximately 28 ATP per glucose molecule with about 40% efficiency, with the remainder released as heat. Understanding mitochondrial architecture is key. The matrix hosts the TCA cycle, while the inner membrane contains the protein complexes that generate the proton gradient across the intermembrane space. It is crucial to distinguish between substrate-level phosphorylation and oxidative phosphorylation. Substrate-level is a faster, low-yield process in the cytoplasm and matrix, while oxidative phosphorylation is the high-yield pathway that sets our aerobic energy ceiling. This overview of the electron transport chain shows NADH and FADH, two feeding electrons through four complexes. Note how NADH contributes to a larger proton gradient than FADH2, which bypasses the complex. I is the largest unit, responsible for NADH oxidation and pumping 4 protons into the intermembrane space. Its dysfunction is linked to conditions like Leber hereditary optic neuropathy. Complex 2 acts as a bridge between the TCA cycle and the electron transport chain. Since it doesn't pump protons, it yields less ATP than NADH-driven entry points. Complex 3 facilitates the Q cycle, a complex mechanism where a bifurcated electron path ensures that protons are pumped into the intermembrane space while regenerating complex IV. 4 electrons reduce molecular oxygen to water. This is a critical step, and toxins like cyanide or carbon monoxide can be lethal here by blocking oxygen reduction. Peter Mitchell's chemiosmotic theory explains the proton motive force as the sum of electrical potential and the chemical pH gradient, providing the driving force for ATP synthase operates like a rotary engine. The flow of protons through the faux rotor drives the rotation of the gamma stalk, inducing conformational changes in the F1 head that synthesize ATP. When counting the total harvest, the PO ratio determines our final ATP yield. Depending on the shuttle system used, the total yield per glucose molecule is approximately 28 to 30 Pharmacological inhibitors target specific complexes to disrupt this chain. Whether it's the pesticide effect of rotenone or the lethal impact of cyanide, each compound offers a snapshot of how proton leaks can have a purpose. In brown adipose tissue, UCP1 allows protons to bypass ATP synthase, generating heat instead of ATP, which is essential for thermogenesis in neonates and cold-adapted adults. Mitochondrial diseases like MELAS and MERRF highlight the impact of mtDNA mutations. Symptoms depend on the level of heteroplasmy, which is why these conditions can be so variable within families. Let's look at clinical impacts like cyanide poisoning and ischemia-reperfusion injury. Both demonstrate the consequences of acute electron transport chain failure. Cyanide blocks complex IV, stopping oxygen reduction, while reperfusion injury involves a sudden damaging burst of reactive oxygen. To summarize, remember these 4 pillars. Electrons travel downhill while protons are pumped up. This electrochemical gradient powers ATP synthesis. NADH is more productive than FADH2, and specific inhibitors help us map the architecture of the chain. That concludes our video on oxidative phosphorylation. If you have questions, please feel free to revisit any of the earlier sections. You can find further reading material listed on the screen to continue your studies. For more information, visit biochemden.com.